So at this point, you have a fairly good understanding of the public interfaces that are defined by the fork join framework, which is, of course, essential to be able to program with it effectively. But we want to go a little deeper. So we're going to take some time now and talk about the internals of how the fork join framework behaves and is structured under the hood. And so we'll see how it implements worker threads first and what those worker threads do relative to these fork join tasks that they're going to process. So first thing to keep in mind, non-fork join task clients, which are the guys on the left, will insert new tasks into the fork join pool's shared queue so it can get into the queue and start to do its thing, or get into the pool and start to do its thing. This shared queue here feeds the work-stealing deques, double-ended queues, that are managed by a pool of worker threads. Now remember, worker threads are actually Java platform threads. They have stack, they have state, they have plenty of things, plenty of horsepower to do the work. Each worker thread in the pool runs a loop that repeatedly scans for subtasks or tasks to execute. So let's say, for sake of argument, we have 3 threads in the pool, and these 3 threads are going to sit there and spin around and looking for stuff to do. The goal of the pool, especially the common fork join pool, is to keep these worker threads as busy as possible. We want them to get a good workout. We want them to burn lots of calories. We do not want them to have to go to sleep if we can possibly avoid it. Each worker thread, which I've talked about a couple times before, has this double-ended queue, also known as a deque, which serves as the main source of tasks or subtasks for it to work on. They call it a work queue in the implementation, but it's really a work deque, just to be aware of that. A deque is just a double-ended queue with some really cool implementation properties in the context of the Java fork join pool implementation, which we'll talk about shortly. So this is what the work queue looks like. And you can see it's got a bunch of methods like push and pop and pull and a bunch of other stuff. We care primarily about push, pop, and pull. If a task run by a worker thread calls fork, or when a task run by a worker thread calls fork, the new task will then be pushed to the head of that worker thread's deque. So we're pushing it onto the head. And the worker thread, once it's finished pushing stuff onto its deque, it processes the deque in LIFO order. You remember LIFO, hopefully, from the data structures class or from lots of other everyday human known uses, like having a stack of trays in a cafeteria. And what goes on first comes off first. So it's last in, first out. And what happens is once the thread is done pushing, it then will say, OK, now I got to do some work. It'll look at its deque. If there's anything on the deque, it'll pop from the head of the deque, and it'll run that subtask to completion. Now, there could be blocking for other reasons because what you're calling might block, but the idea is that that worker thread will just keep doing its thing on that particular subtask in its compute method, for example, until it's done. When if/when that worker thread, the code in the worker thread calls join, then that thread will pitch in and execute the subtasks using the Jiffy Lube model of collaborative processing that we talked about before. Why does the fork join pool do LIFO ordering on the task it's working with? Well, the reason is we want to improve locality of reference and cache performance. What does that mean? What that means is that when you push something on very recently, chances are when you pop that thing off, it's still going to have its instructions and data in the processor cache, just because of the way that caching works. You typically keep some stuff around, and so this is what's called locality of reference, and it's a way to optimize cache performance. Doesn't always work, but it's a good heuristic, and therefore that's why they do the LIFO model. So that's the end of the overview of the worker threads portion of the Java fork join pool internals. We will then talk next about stealing, which is also super cool. And when we talk about stealing, you'll see that when we steal, we end up stealing from the end of the deque, whereas one thread will steal from another thread's deque by stealing from the end, and we'll talk about why that is. But normally, a worker thread will push and pop on the head of the deck.